This video is intended to be watched after you've completed this math lab. So in this video, what I'll do is I'll go through the math lab, not completing all of it, but hitting the highlights from each part, and then adding on a little bit of extra information just to round out our understanding. To begin with, you'll note here a definition that I've written down that is in your workbook on page 514. A function that repeats its values in regular intervals over its domain is called a periodic function. The length of each interval or cycle, measured along the horizontal axis, is called the period of the function. And so as you graphed this three functions, y equals sine x, y equals cosine x, and y equals tangent x, each of these was a periodic function in that they repeated themselves over a given interval in the horizontal axis. So let's review these three together. When you looked at the graph of y equals sine x, you were given this table to complete. Now I'm not going to complete the entire table, I'm just going to highlight some of the most important points that we want to be able to make use of as we sketch the graph. The most important points that we want to be able to put on our graph every time starts with when x is 0, the sine of x is also 0. When x is pi by 2, the sine of x is 1. When x is pi, the sine of x was at 0 again. When x was 3 pi by 2, the sine of x was negative 1. And when x was 2 pi, the sine of x was 0. So this was one complete period, or one cycle, of the graph y equals sine x. So let me begin by plotting these 5 points on the grid below. So the sine of 0 is 0. The sine of pi by 2 is 1. The sine of pi was 0. The sine of 3 pi by 2 was negative 1. And the sine of 2 pi was 0. So those are the 5 important points that we want to make sure we get on every graph. But there are a few more that, to be a little more precise, we could sketch as well. So let's look back at our table for a moment. The sine of pi by 6 is 1/2. And the sine of 5 pi by 6 is also a half. The sine of 7 pi by 6 is a half, and the same with 11 pi by 6. So this gives us 4 more points that we can make use of as we sketch our graph, just to add a little more precision to the curve. So plotting those, we have this point, this point, this point, and this point. So now we have 9 points to sketch our graph from, and a quick disclaimer here, drawing with this app is not the easiest thing, so my curve may not look great, but yours should look better than mine. So here we'll have the curve going down. Whoop, squiggling a little bit there. And there we have the rest of the graph. So that's one complete cycle, or one complete period, of the graph of y equals sine x. Again, yours hopefully looks a little less squiggly and spidery than mine, but that gives us the idea. Now we want to look at some features that weren't included as part of the math lab, but are important for us to understand, and so you might want to find some space where you can write this down. So we'll look at the domain and range to begin with. For this question, we were only asked to sketch the graph for x values from 0 to 2 pi, but if we weren't given that restriction, the domain for this function would be that x could be any real number. The range, we can see our y values oscillate from a minimum of -1 to a maximum of +1. Our y-intercept is at 0. And the zeros for this function, we'll see here we have a 0 when x is 0, when x is pi, when x is 2 pi, and that pattern will continue. And so we can write that we have zeros at n pi, where n is an element of the set of integers. Again, integers, positive whole numbers and their opposites, so -2, -1, 0, 1, 2, 3. So any multiple of pi, where we have integers multiplied to pi, those are going to be x-intercepts or zeros for our function. The amplitude is looking at the distance from this line, which we could call a center line, or a midline, or a median, sometimes an equilibrium line. So the distance from that line to a high point, or the distance to a low point. And so we would say the amplitude for this function is 1. So here, that much is our amplitude. Our period is the horizontal distance for one cycle. So from some point on the graph until it starts repeating itself. So for this graph, this will be our period. So the period is 2 pi. And then I've already referred to the median or the midline. In this case, it's that horizontal line y equals 0. And we can see that from this line, the graph oscillates equal distances above and below that. And so we call it the median. Your book tends to call it a center line, but a variety of different terms could be used. You should be familiar with them. And as we go through, I'll be using a variety of them, so you will get to know them. Okay, so there we have the graph of y equals sine x and some of the key characteristics. Let's move on to the next graph of y equals cosine x. As we look at our table of values, we'll see a similar pattern as what we had with y equals sine x. So when x is 0, the cosine of x is 1. When x is pi by 2, the cosine of x is 0. And then at pi, the cosine is -1. 3 pi by 2, we're back to 0. And at 2 pi, we're at 1. And then finding those additional points that will help us get a slightly more accurate graph. At pi by 3, cosine is 1/2. And at 2 pi by 3, the cosine will be -1/2. For pi by 3, we're at -1/2 again. And at 5 pi by 3, we'll be at +1/2. So let's plot these 9 points on the grid. At 0, cosine has a value of 1. Pi by 2, it's at 0. At pi, we're at -1. 3 pi by 2, we're back to 0. And at 2 pi, we're at the maximum value of 1. Putting in those other 4 points, we get them at those locations. And again, the shape of our graph will be similar to the shape of the sine graph. It's just got a different starting point. And again, your graph will hopefully look better than my graph. But there's the basic idea. And again, from this graph, we can list out some of these key features. We were only asked to sketch the graph over the domain from 0 to 2 pi, but if we weren't given that restriction, then again we'd have x could be an element of any real number. Our range, -1 is our minimum, and 1 is our maximum. Our y-intercept is now at 1, so that's different from the graph of y equals sine x. The zeros are also different, so as we look at these points, we'll see here's our first 0, which was at pi by 2. Our next one was at 3 pi by 2. And so looking at the distance between these two, that distance was pi radians. And so again, every 0 will be separated by pi, but this time we'll need to write down that our first 0 happens at pi by 2, and then we can add multiples of pi to that. So this is a plus sign. And as before, we'll say that our n value needs to be an integer. Similar to the graph of y equals sine x, we have an amplitude here, which is from that median or midline. Maybe I'll write that in right away. Again, the median or midline is y equals 0. Our amplitude will be 1, and our period, this distance from some point on the graph to where it starts repeating itself, that period is 2 pi. So similar features and characteristics to y equals sine x. Key difference is the y-intercept, or the starting point for the graph, and where the zeros occur. All right, let's move on to y equals the tangent of x. So here are the key parts of the graph. When x is 0, the tangent of x is also 0. At pi by 4, the tangent of x is 1, and then at pi by 2, it's undefined. So at that point, we're going to have a vertical asymptote. At 3 pi by 4, we'll be at -1, and at pi, we'll be at 0. 5 pi by 4 will be +1. 3 pi by 2, again, will be undefined. So you should already have this from when you work through the math lab. And then a couple more points that we can put onto our graph. So let's sketch it to see what it looks like. Let me start with the asymptotes, and I don't have a straight edge, so yours should look better than mine once again. Or maybe not. I found a line tool. I should draw them as dotted lines, but couldn't find how to do that with this app. But I have a point here, and then halfway in between here will be where pi by 4 is. And then here I have another x-intercept. There I'm at 1, and here I'm at -1. There I have an x-intercept, and here I'll be at -1. So let me draw this middle curve first, because that'll give us a little bit more of the shape. So it curves like this, and curves up like that on the other side. So it's approaching the asymptote. So hopefully you can do a better job. The curve going here, and the curve going up there. So it's approaching the asymptote. Where it crosses the x-axis, it doesn't go to horizontal. It curves a little more than I showed at 2 pi. The middle one's not too far off. When you enter these graphs on your calculator, you'll get a better picture. But we'll call that good enough for now, given this app. Going through and listing out the domain and range. So domain is going to be a little bit different this time because we have these points where the function's undefined. And so the first point where it's undefined is at pi by 2. So we'll say x can't equal pi by 2, or again the distance between these asymptotes is pi radians, so multiples of pi, or again we'll say n is an element of the set of integers. Our range, y can be any real number. So x is any real number other than ones that are listed there. I'm just out of space for me to fit it in. The y-intercept is at 0. I'll just do a different color here so we can keep that clearer. The period, now from where the graph starts to where it repeats itself, well, here I can look at there. It starts on the x-axis and then curves up. Here it's on the x-axis again and curves up. So now our period is pi radians rather than 2 pi. The zeros happen at 0 and pi and 2 pi, so it'll be similar to the graph of y equals sine x. So the zeros are at n pi, where n is an integer. And the asymptotes will be similar to what we wrote for the domain, but this time we'll use an equal sign where x equals pi by 2 plus n pi, where n is an element of the set of integers. Okay, so there we have a look at those 3 primary trig graphs and some of the key features of them. So that's the end of this video. Time for you to move on, work through another question, look at some graphing and see what happens when you change some of the elements in the equation, and then come back and watch the next video. All right.